Good morning, students. Myself, Dr.BADI ALEKHYA, Associate Professor, Department of Artificial Intelligence and Machine Learning, R.M.D. Engineering College. In the previous session, we discussed what are the different types of feature extraction technique, what is the purpose of using feature extraction technique in your machine learning algorithms. So, among that thing, today we are going to discuss one numerical example of principal component analysis, which is used for dimensionality reduction and the feature extraction mechanism of your feature engineering. So, let us proceed with the numerical example of principal component analysis. So, they are giving a data set in the given table consisting of two features. The two features, one feature consisting of 4 samples and another feature consisting of 4 samples, totally 8 samples. So here, what is the motive of using principal component analysis for this data set is we are going to convert this two-dimensional data into one-dimensional data. So let us proceed with the steps. So first we have to construct the data matrix. So under data matrix for the X samples we have 4, 8, 13, 7 that we are representing in column wise, and for the Y components we are going to represent 11, 4, 5, 14 here, 11, 4, 5, 14. This is we are going to construct the data matrix, and then second step we have to compute the mean of each features. How to compute the mean of each features means in the first feature we have a data samples 4 plus 8 plus 30 plus 7. By adding these things and divided by total number of samples, we are getting a mean of 8.0. And for the same like that for the second feature also we have to calculate the mean. The first step is you to construct the data matrix, and the second step you have to calculate the mean for the each feature. And move to the step 3, we have to consider the data. How we are consider the data means simply we have a covariance matrix build up is there. Under the covariance matrix we have to calculate the covariance between x comma y, y comma x and y comma y. That is x comma x you are generating, that is nothing but variance of x. You have to performing this means you have to minus that mean between the data points, you have to perform minus, and if you have to calculate that mean, you will generate a value of 14. Between x and y you have to consider both the points when you are performing multiplication, and you have to substitute. So for variance x and y we have to consider the same data point and we have to perform the subtraction, and for the x comma y and y comma x we have to considering the difference between both the points. I will explain because x comma x and x comma y is easy. If you are considering x comma y means you have to separate 4 minus 8 and 11 minus 8.5. 4 minus 8, what's the value here? It's a data point. If you are performing x comma y means 4 minus 8.0. If you are considering second y means 11 minus 8.5. Like that you have to substitute minus 4. That means 4 minus 8 is representing minus 4. And coming to the back point, 11 minus 8.5 will generate 2.5. Like that you for each and every variable you have to perform like this and generate the answer 11. So under step 4 we are going to compute the covariance matrix. I repeat it. In step 1 we have to construct the data matrix, and step 2 we have to calculate the mean, and step 3 we have to consider the center of data and compute the covariance matrix. In step 4 we are designing the covariance matrix, which is representing the element values as 14 minus 11 minus 11 23, and then we have to compute the eigenvalues. To compute the eigenvalues we have a formula, determinant of c minus lambda I, and after substituting it in we have to calculate expanding this equation by multiplying cross product is their Cartesian product and generating the equation. Based on the equation we have a quadratic formula to identify the lambda values. Here I didn't represent the values. If family that formula b minus b plus or minus square root of b square minus 4ac. That formula we are applied and we are calculating the values of lambda here minus b plus or minus b square minus 4ac divided by 2a. Values are there. We substitute in it and we calculate lambda 1 and lambda 2. And finding the values, after that we substitute. Here in this principal component value for principal component analysis, here we have two eigenvalues generated. No need to calculate for the two eigenvalues. Under principal component we are giving preference to the highest eigenvalues to convert two-dimensional into one-dimensional. Among these two things, which one is generating highest eigenvalue? Lambda 1 is generating the highest eigenvalue. So considering that eigenvalue, I substitute in the equation to generate eigenvectors. After substituting in the equation, it is generating the eigenvectors. So it's a simple procedure to elaborate how we are generating eigenvectors. After substituting in the equation, we are getting first equation, second equation like that. From first equation, I am going to consider 14 minus lambda I u1 and 11. When we are considering first equation, it will be representing it as 11 mu2. So mu1 divided by 11 cross and 11. This we are going to assign to some constant. This constant we take it as 1. And if you are calculating eigenvector 11, 14 minus lambda 1. What is the lambda 1 value? We already calculated lambda 1 value, that is 30.3849. If you are minusing that lambda value, it is generating 16.3849. So after generating that thing, you have to normalize that eigenvector by dividing with both value 11 divided by square root of 11 square plus the second eigenvector value is 16.3849 square. If you are performing like this, you are generating eigenvalue. After calculating these eigenvalues only, we can able to generate the new data set which is used to convert two-dimensional to. For this problem, we are converting the two-dimensional to one-dimensional. We already generated eigenvector 1. We have to perform transpose for this value and the new data point, that already existing data points are 4 and 11. If you observe at the data set initially, what is the first data point here? 4, 11. That 4 we can minus from 8 and 11 we can minus from 8.5. And it's generating a value minus 4, 2.5. If you are multiplying that thing, you can get the principal component P11. Like that, you can calculate for all other data points available in the data set. If you observe here, the original data set is 4, 8, 13, 7, 11, 4, 5, 14, consisting of 8 samples and 2 features. Now, after applying the principal component analysis, the 8 features is converted into 4 samples. 4 samples means now I am reducing two-dimensional to single dimension. That is the purpose of using feature extraction mechanism, principal component analysis in the machine learning algorithms. That's all, students, for the today's session. I will meet with some other new concept in the next session. Thank you all.